Hello everyone! Thanks for joining to watch 5th add-on video for Why Algorithms topic. In the previous one, we moved from graph use cases to implementation of graphs and connectivity group use cases. We mentioned breadth-first search and depth-first search algorithms, introduced connected component API, and finally checked how to find minimal spanning tree using couple of possible Kruskals and Prim's algorithms. Let's move to path use cases group. First use case: is there a path between S, source vertex, and T, target vertex? FYI, let's start with undirected graph. If you plan to ask such question several times for different pairs of vertices, but for the same graph, then it probably makes sense to preprocess graph and discover all connected components. We discussed it in the very previous add-on video. Did you already guess how it could be helpful? You can have paths between two vertices only if they belong to the same CC, connected component. Preprocessing for CC can answer the main question, is there a path between two vertices, without providing path itself, list of edges. If you plan to ask questions several times for the same starting vertex S for several different target vertices, and additionally want to know path from vertex S to target vertex T, then another connectivity use case could help. The very first we discussed in the previous add-on video. Find all vertices connected to a given source vertex S. We introduced two APIs to preprocess graph to form spanning tree. Remember APIs for BFS and DFS. All that we need to do to add extra function named hasPath2 with input parameter T, target vertex. Source vertex is already known once preprocessing was done from source vertex S. If you remember, at preprocessing step, algorithm saves parent vertex from array, which allows to reconstruct path all the way from target vertex T to the source vertex S, which is a root node of our preprocessed spanning tree. After DFS, BFS, we can find vertices connected to S in a constant time and can find path to T, if one exists, in time proportional to its length. If you plan to ask a question just one time or rarely occasional, then to speed up process, you can implement own function using ideas from BFS or DFS. Instead of bringing all vertices into a spanning tree, which can be reached from vertex S, you can stop algorithm execution right away once target vertex T is reached. Which API to choose, BFS or DFS, depends on your preliminary estimation, how target vertex T is closed to source vertex S. If target vertex T is closed to S, then DFS may spend a lot of time discovering far routes before reaching vertex T, which means there is a high chance your DFS algorithm ends up spending more time than BFS would do. That was about path in undirected graph. Please check yourself which path use cases just discussed for undirected graph are applicable to directed graph. We don't plan to talk about it in this video. First path use case is done. It was about, is there a path between S, source vertex, and T, target vertex. Let's move to the next two path use cases, and we will focus on directed graph for them. What is the shortest path between S, source vertex, and T, target vertex? And next, what is the list of shortest paths from S vertex to all other vertices? If we would be able to preprocess our graph to answer a question about list of shortest paths, then particular path among others preliminary discovered can be found quickly. Let's start with list of shortest paths task. This is actually about finding shortest path tree. Our API to consist from preprocessing function sp3 to find the list of all shortest paths, or shortest path tree in other words, which takes input parameters, graph and started vertex S, and additional useful functions, path2 to find shortest path from vertex S to vertex V, and some auxiliary functions for convenience, like dist2 to retrieve shortest path from S to V, or hasPath2 to check is there a path from S to V. That's about abstract API. Implementation of preprocessing function can be done using several generic shortest path algorithms. For example, Bellman-Ford algorithm. But one of the most efficient known one is Dijkstra algorithm. There is a restriction to use Dijkstra algorithm. It computes SPT, shortest path tree, for edge-weighted D-graph with non-negative weights only. You cannot use it if some edge weight of a graph is -1 or -10, for example. Here is our graph with weights assigned to its directed edges. The main idea of Dijkstra algorithm is based on so-called edge relaxation mechanism. This mechanism allows eventually to find edges to be included in SPT. Let's check how exactly. Mechanism maintains two important parameters for each edge in the graph. First parameter, dist2, is overall current distance to vertex from starting point S. Let me write values for some vertices. And second, edge2 parameter describes current incoming directed edge which used to reach particular vertex on the way from starting point S. Word current used intentionally, since list of edges could be changed several times during algorithm execution. Edge relaxation mechanism is applicable to any vertex which has alternatives in incoming edges. All vertices in our graph have just one incoming edge. The only exception is vertex 6, which has 4 incoming edges. So mechanism is applicable for vertex 6 in our case. It selects each edge one by one till shortest path to vertex 6 is found. Order of traversing incoming edges is out of scope for now. For our example, let it be from bottom to top. Initially, current edge to vertex 6 is absent, and current distance to vertex 6 to be infinitely large. Then algorithm selects current edge 4 to 6 and calculates current distance to vertex 6 through this edge. This distance is shorter than infinite large. Therefore, we select edge 4 to 6 for now, as giving us shorter path. We know it's not the shortest distance from 0 to 6 though, but algorithm does not know yet. It needs to verify other alternatives. It checks next incoming edge candidate 5 to 6 and finds overall distance is shorter, overwriting current edge 2 and distance values. Similar actions to the next incoming edge 2 to 6. Algorithm checks the last candidate edge 3 to 6, but it's not making overall distance shorter. So our values stay intact. What we just did, we selected edge 2 to 6 to be included in SPT among 4 candidates. Edge relaxation mechanism can be analogically compared with metal spring tension. The longer spring is stretched, the more it's tensed, and stronger it tries to shrink. The shorter spring is, the more relaxed it is. By selecting incoming edge on each step, we feed our spring all the way from starting vertex S to current vertex, 6 in our example. If other edge gives overall distance from vertex S shorter, our spring feeds on the new path and becomes more relaxed. Step by step, till the most possibly relaxed spring, meaning shortest path, could be found. From this point of view, edge relaxation naming convention is not precisely accurate. Technically, we're relaxing the whole path to vertex from starting point by selecting alternative last mile incoming edge. Probably it would be more accurate to name mechanism path relaxation. Anyway, I've just described algorithmic approach for that relaxation, which should be the main supportive function for Dijkstra algorithm. Relaxing, relaxing and relaxing till finding edge to be added to SPT. Let me start writing Dijkstra SP3 API for it. A relevant supported function relaxed path in our overall API for Dijkstra algorithm can look as simple as this one, just taking one directed edge as a parameter to check would it be possible to relax a path to vertex this edge is pointing to. Let me also explicitly write supported parameters to be stored. Edge to array, which stores edges to vertices which could dynamically change while algorithm executing, ultimately represents edges for the shortest paths. And dist to array parameter, which stores distances from starting vertex to all other vertices. Also may be dynamically changing till shortest path tree is finally built. By the way, we already discussed relaxed path function implementation a minute ago. It was a simple example of relaxation for a graph which has just one vertex with several alternative incoming edges. In practice, there might be a lot of such vertices in the graph. When algorithm makes a decision, it's important to rely on complete input data on certain steps, so this data should not be changed later. For example, if algorithm finally selected edge from 2 to 6 to be in SPT, distances to vertices 4, 5, 2, and 3, all connected to vertex 6, should not be changed after edge 2 to 6 selection, because it potentially can bring a situation that edge 2 to 6 towards vertex 6 might need to be replaced by another one, bringing shorter distance to vertex 6. Here we need to start discussing how main preprocessing function of Dijkstra algorithm to build SPT should work. This is about Dijkstra SP3 function in our API, which takes edge-weighted dgraph G and starting vertex S as input parameters. To understand what to be the outcome of the algorithm, let me show how final SPT should look like with all values for each vertex filled for overall distance and last mile incoming edge. Generic algorithm to compute SPT from vertex S may consist of two main steps. Initialize distances from starting vertex S, dist2 for starting vertex S is 0, and dist2 for all other vertices V as infinite. Second step, repeat relaxing edges until certain conditions are satisfied. Going from generic to Dijkstra algorithm implementation. Conditions to stop edges relaxation and order of visiting vertices on each step will be in focus. How it works? Dijkstra algorithm works in iterations. On each iteration, it works with just one outgoing vertex of a given graph. I named it outgoing to stress out that we will look to edges pointing out from such vertex. I separated each iteration for simplicity into 3 sub-steps. First step, with focus on order of traversing to select vertex. Initially, all vertices are considered. At the end of every iteration, we remove one vertex from further consideration. Algorithm considers rest of vertices in increasing order of distance from S, which means algorithm selects vertex with the smallest dist2 value on this first sub-step. For the very first iteration, starting vertex S to be selected, since it has the smallest value of 0, while others have infinite large. Second step focuses on edges. Supportive edge relaxation function to be used on this second step. Dijkstra algorithm relaxes paths using all directed edges, if any, pointing out from a prior selected vertex. If outgoing edge relaxes path to its destination vertex, then such edge should be added to our dynamically building SPT. Adding to SPT means it's either newly added or replacing other edge for the same destination vertex previously added to SPT. Remember, we discussed vertex 6 a minute ago and replaced edges couple of times till final one was found. For our graph, on the first iteration on this substep, we newly add all 3 outgoing edges from vertex S, since they all relax overall paths to respective vertices 1, 6, and 4. Just FYI, remember greedy type algorithms like Kruskal's from previous add-on video, they don't reconsider selected sub-results on later steps. Dijkstra is not algorithm of a greedy type, right? Dijkstra algorithm may replace one edge by another while building SPT because of a relaxation function, not greedy. Third and last substep. At the end of iteration, outgoing vertex selected on a first substep is taken out from future iterations consideration. In our example, we remove vertex 0 or vertex S. And algorithm goes to the next iteration, selecting vertex among left with the smallest distance from S. For example, vertex 1 to be with the shortest distance 5, among others. I hope you understood principle of Dijkstra algorithm. I don't plan to go through all steps for our graph. but just want to show example of replacing edges in SPT graph. When outgoing vertex 1 is selected, we adding edges 1, 2 and 1, 3, since they relax paths to vertices 2 and 3 from S. Take a look to final SPT for a while. You can guess on later algorithm steps, when outgoing vertex 5 will be selected, edge 5, 2 will replace 1, 2. And when outgoing vertex 2 will be selected, edge 2, 3 will replace 1, 3. One more thing to perfect our Dijkstra algorithm implementation topic. Remember reduction technique to separate overall task into subtasks and solve each one the most effective way. Let's not to reinvent the wheel and spy for the best practices. When I watched video course from Princeton University by Robert Sedgwick and Kevin Wayne, they gave implementation idea how to handle subtask of having vertex with the smallest distance to value always handy, and how to quickly remove such value from the list of considered vertices. Do you guess which API they suggested? It was among some ideas discussed earlier in our videos Why Algorithms add-ons. If your thoughts were with PQ, priority queue, you are on the right path. But PQ originally takes care of set of vertices of similar type and has two main functions, insert item and delete minimum or delete maximum, returning and deleting element of a minimum maximum value, depending on what type of PQ implemented. For our Dijkstra algorithm, we work with pair of parameters, vertex number and corresponding distance to value. We don't need to know just the smallest distance to value itself, which can be done by functionality of standard PQ. Actually, we need to know corresponding vertex number relevant to the smallest distance to value. Let me show you suggested API for special PQ, in fact special MinPQ, since we are interested in the smallest value always available. It contains two adjusted main functions and two extra supported functions for Dijkstra algorithm. Let's see our special MinPQ class. Insert main function inserts into PQ vertex number and corresponding distance to value. Another delmin main function returns vertex number with the minimum distance to value. And couple additional functions, decrease key, to decrease overall distance from starting vertex to current vertex given as an input value, along with corresponding dis2 value. And another contains function, which checks do we have a vertex number in our PQ. Original PQ is focused on working with the set of the only one data type. And PQ's main and the only efficient functionality is to return the minimum or maximum value among all inserted. Original PQ does not have implemented efficient searching functionality for specific value, and we want function contains to be implemented to search. Moreover, it searches not for the value in our main focus, distance 2, but for corresponding paired value of different type, which is vertex number. How to improve, complement PQ implementation to reflect our modified and new API functions. My first personal assumption was about bringing key value pair functionality handling for effective search, using symbol table API discussed earlier in our videos as well. This assumption came from an idea that we can name vertices using generic type of data, for example string type with random values. But instead of generic data type, Robert Sedgwick and Kevin Wayne suggested more elegant solution, which is based on simplification discussed earlier when we just started discussing graph functionality. Graph vertices is easier to represent by integer numbers, and we can have even stronger boundaries. Instead of any random values to represent vertices, we can agree to use consecutive integer numbers, starting from value 0. Numbers 0, 1, 2, 3, etc. look like an index for an array values, isn't it? So we have vertices numbers taking values of index from 0 till max number of vertices in a graph, -1. And for such simplification, effective implementation could be found for our adjusted PQ API. Let's rename our API to IndexMinPQ, stressing out that we will work with index numbers linked to our initial key values. We don't plan to discuss IndexMinPQ implementation in this video. I will provide link for your curious minds at the end of the video to analyze code yourself, if you want and whenever you're ready. But imagine, for example, how simple to implement contains function if you know that you have limited amount of vertices, n. You can add and maintain extra array, for example inserted, of size n, initially set all its values to boolean value false. And when later you insert vertex to IndexMinPQ, corresponding array's value is to be overwritten for boolean value true. And function contains can be as simple as just one step. Returns true, which means vertex was added to PQ, if this extra array's value at vertex number position is equal to true. For example, on the first step of Dijkstra algorithm, we insert in our IndexMinPQ information about starting vertex S with index 0. And internally corresponding value of inserted array should be overwritten along with saving distance to value into separate binary heap structure, natural for PQ API. If you forgot about PQ, you can check our previous video Why algorithms. Now, if we want to check does our IndexMinPQ contains vertex 0, function contains returns true, meaning vertex 0 is in our PQ, because inserted at index position 0 associated with vertex number 0 is not equal to false anymore. For decrease key function, trick is more sophisticated. We not only need to find vertex, but also override corresponding distance to value. In original PQ implementation, binary heap likely change positions of values in a heap each time we add delete value to have certain order and minimum value immediately available. That means if we would implement our IndexMinPQ similar way, after few operations, distance to value likely won't be stored on initial position in a binary heap. Then how to effectively replace distance to value for vertex keeping PQ functionality in place? Answer is, since vertex numbers are indexed and have limited values, we can introduce extra key array storing just keys, distance to values. And which is more important, values of this array to stay in place. So later we can easily overwrite decrease key value fast enough. But to keep PQ functionality, we need to introduce additional PQ array, which values will be pointing to key array. And PQ array, instead of key array, will be actually shuffling its values, pointers, according to PQ rules when we add delete values. We didn't discuss full implementation details, but shared main ideas for Dijkstra algorithm, which builds SPT. We discussed edge relaxation mechanism, which eventually helps to find edges to be included in SPT. Once graph is preprocessed, we can answer path use case question. What is the list of shortest paths from S vertex to all other vertices? How to answer another path use case question. What is the shortest path between S, source vertex, and T, target vertex? It can be done easily after preprocessing by Dijkstra algorithm, just discussed. We can add extra function into our API, path2, which takes vertex index and returns list of directed edges. This function should return set of edges connecting starting vertex S with target vertex T. How to implement it? Just look closely to parameter values prepared after graph preprocessing. Pick any target vertex, for example 3. How difficult is to find set of edges included in the shortest possible path from S to T? You probably guess. We just need to make back trace of edges from target vertex all the way to start vertex S. Now we can consider topic about ideas for path group use cases as closed. We can answer questions: is there a path between S and T? What the shortest path between S and T is? What the list of shortest paths from S vertex to all other vertices is? For the first question, different approaches were discussed for undirected graphs. to use preprocessed connected components, to use preprocessed spanning tree built by BFS or DFS, breadth or depth first search algorithm, with extra function has path 2, with input parameter vertex number, or to use BFS DFS algorithm, which stops right after answer is found, if any. For second and third questions, Dijkstra algorithm for building SPT from directed graph was discussed. We discussed edge relaxation mechanism, new parameters edge2 and dist2, which help to implement this mechanism, and additionally discussed IndexMinPQ API, which allows to help with graph vertex order traversing. Consider vertices with the smallest dist2 value on each step. Limitation for Dijkstra algorithm: graph weights should be non-negative only. For graphs with negative weights, Bellman-Ford algorithm to be used instead. Not discussed in this video though. Now let's move to cycle group of use cases. Most useful one: is there a cycle in the graph? The answer is either yes or no. One of the possibilities to solve this task is to have an auxiliary information coming from DFS algorithm. If you remember, when we traversed initial graph, analogical example was used: unrolling ball of string. When we were unrolling it, we were moving forward and forward, discovering some path. And at certain point we need to temporarily move back, kind of trace string back. What might be a turning point between unrolling ball of string and tracing it back? One possibility is we may reach a leaf vertex with no other edges out of it, but the only one which we came from. Another possibility is that outgoing edge is connecting us to a vertex which we already visited on the previous steps of the algorithm through different paths. Do you remember Boolean array marked, which we used to mark all visited vertices? For DFS algorithm, it's important to move back at this point, because algorithm shouldn't build cycles. Its outcome is a tree without cycles. Returning back from DFS connectivity group use case to our current cycle group use case. Once DFS algorithm reached marked vertex, visited earlier, is there a cycle in the graph question immediately can provide yes answer. Do you agree? If DFS algorithm was ended, which means it visited all possible vertices within connected component, assuming graph has just one connected component, and in the meantime none of the visited vertices was reached second time, then is there a cycle in the graph question should return no answer. Agree? That's how we can solve cycle group use case. For Euler tour use case, is there a cycle that uses each edge exactly once? The answer is connected graph is Eulerian if and only if all vertices have even degree. Remember degree term? It's about number of edges to vertex. So for this graph, we cannot find an Eulerian cycle, because at least this vertex does not have even degree. Another Hamilton tour use case with the question, is there a cycle that uses each vertex exactly once? It's actually intractable task. It's enough for this video for cycle group use cases. We finished some implementation details of path and cycle use cases groups. We have last topic to be discussed in add-on video 6 for Y algorithms discussion. It will be about flow and capacity use cases. Ready to dive deeper? Then see you there!